Good morning. I'm talking about these topics mentioned by the chairman. So the frame of this research is the aeronautic field, where, as you know, we have a combination of multiple materials, in particular metal parts for structural components, especially aluminum alloys components, and composites for especially for the shaping of profile or for other minor structural components. Of course, we also have some other complicated and complex structures like honeycombs and sandwich panels. And in general, we have different methods for joining these materials, including mechanical joints like rivets or adhesive means. And in both cases, we need to respect very stringent normative requirements, standard requirements that are related to the materials that must be qualified for aeronautic field, the testing methods, and also the fabrication process for aeronautic field that must be also qualified before. So the aim of this research is to provide some new design concept for the next generation aircraft that will be addressed to increase the environmental sustainability. And this sustainability is applied to flight operations, including, of course, reduction of emissions and optimization of weight. That means innovative structures. Also dedicated to the production phase by the shortening of the manufacturing chain and again, introduction of coupled technologies, merged technologies with innovative design solutions. And of course, new materials, including recycling and regeneration of materials and secondary raw materials. So the typical structure of a primary flight control structure, for example, is like this one, where you have we have metal components like ribs, spares, stringers, and so on, and other composite parts like the external skin and other minor elements. I mentioned the riveting means to join the material. So rivets have some problems. First of all, the weight on a traditional medium-sized aircraft for passengers, we have about 100,000 rivets. That means about 120 kilograms only for the rivets. That is a lot. Then also we have holes in the skin that reduces the structural integrity of the composite. A long manufacturing time to produce and join this skin, about 15-20 manufacturing steps are needed. And also the use of chemical paints and other treatments that have high disposal issues and impact on the environment. So what we are trying to do is to find a new way to build aerostructures for the new generation of aircrafts. And so we started this research and innovation project a couple of months ago that is called Mimosa, multi-material airframes based on 3D joints between additive manufacturing metals and carbon fiber composites. That starts from a couple of patents we deposited at Politecnico di Torino in 2019 and 2020. After that, we built a consortium of industrial partners to find a way to provide innovative solutions regarding these new requirements. So we are the coordinators of the project. We have Leonardo as a market driver and end user of the structures, TÜV that works about the regulation of the standards requirements, and a number of other technological units providing the different steps of the production. What we want to explore is the possibility to join the two materials without rivets, without adhesives, by using a co-curing method of metal inserts inside the composite. So the metal parts are fabricated through additive manufacturing processes, including shape complexity on the surface with the building of small three-dimensional anchors on the surface that are able to grip and to mechanical constrain the fibers of the carbon fibers of the composites, and so to provide an engagement without external mechanical parts. Of course, we need a lot of intermediate complicated steps like surface coating of the metal to prevent galvanic corrosion, to improve the wettability with the composite, and many other steps. What we have here is just a very preliminary investigation about the global behavior of this kind of joint, where we have some numerical modeling based on a couple of strategies. Letter A is based on the real geometry of the joint, so 2 volumes only. The letter B is referred to another strategy with an intermediate volume composed by a mixed weighted mixing of properties of anchors and the composite material. Another solution is a homogenization approach. We have used for this preliminary study some material properties measured directly by experiments. On the lower part of the slide, you see a module that is corresponding to one of these anchors. In this case, is a cubic anchor. That means that we can use a modular approach by studying just one module and to, of course, repeat the effect on the whole surface. Of course, the topics of interest are, first of all, the number, the shape, the density, the orientation of these anchors, which one is better to provide the best strength of the joint. Then also the transition, the local transition of stress, strain, and the mode of force transition between the metal part and the carbon fiber, and of course the failure modes of the joint. So very preliminary experimental investigations that just to understand how much is, so the amount of force that can be transferred. So we built the metal part with additive manufacturing process on a rainy show machine. Here I have listed the printing parameters, and we built the joint by laminating the composite in the laboratory in an ambient condition with 24 hours of polymerization time. And we performed some static tests just to compare so the effectiveness of these models. So out of 5 samples, we get some repeatability, first of all, of the mechanical response in static conditions. We get pretty high values of the load transferred, so it's good. And also our models are calibrated, are well tuned on the experimental results. So this is just a focus on the very first preliminary investigation. We are starting the project right now, and so we will expect in the next month other results. So this is my references. If you have questions, we don't have time now, but I'm open, of course, to reply to your eventual answers. Thank you.